Visualizing data is one of the key reasons why many scientists use Python. As we've seen in the previous video, to store data we need arrays. And for arrays in Python we use the module called NumPy. And from NumPy we can also load data from a file into an array using the NumPy command load text. Conversely, we can also save data from an array called data, for example, to some file name. Besides loading measured data from files, we can create our own data using functions. For example, using NumPy's linspace, we can create a linear list of numbers from which we can use as the inputs to a function, such as numpy.exp for an exponential function, or indeed for any other function we would like to define ourselves. We can of course also use NumPy to organize the data. For example, we can take two arrays such as x and y and combine them into a single array using NumPy's array command. We can also join arrays together using concatenate, and this is useful if you generate some new data and you want to add it to your existing data set. Besides increasing the size of our arrays, we can also make them smaller by dividing them into subcomponents. While we can do so using our slice commands, where we use the index and a colon symbol, we can also use specific NumPy commands, such as vsplit, which divides an array into, in this case, two parts along the first axis. If you wish to flip the rows and columns of your data arrays, you can of course use transpose. Here we will swap the 4x2 array into a 2x4 array. Once we are comfortable storing our data in arrays and manipulating those arrays, we can start looking at visualizing the data. To begin, we will look at 2D visualization. And for all our visualization needs, we will use the module matplotlib, which contains pyplot. And pyplot here is imported as PLT. And for an initial example, we'll create some data for a projectile motion. And here we've got our time array from 0 to 10. That will give us 50 data points by default. We can define some variables for velocity and acceleration. And the height of our projectile we can just simply calculate using our time array. To visualize the data with matplotlib, you essentially use the simple command plot. And this generates a 2D visualization of height and time. The basic syntax for the plot command includes starting with the x data, y data, defining some style of the line, and also providing a label which you can use later for a legend. In our next example, we will add a second curve or second data set to this plot. First, we will define it and we will change the velocity in our projectile motion to 20 meters per second. Once we've calculated the height y2, we can of course visualize it using plot t y2, and this adds the second curve to our initial plot. As we can see, the second projectile has fallen below the 0 level, and this begs the question, can we change the y-axis limits? With matplotlib this is very easy. There is a command called ylim, where you provide the initial limit for 0. If you leave the second blank, it will use what it thinks is optimum. Conversely, there's also an x limit or xlim command for the x-axis if you want to vary the scale there. Besides the limits of the axis, you can also label the x and y-axis using x label and y limit label respectively. Here I've labeled the x-axis with time and seconds and the y-axis for height and meters. Next, to see how we can create the legend for the label, we can write out the full plot commands for y and y2, and here you'll notice I've included a label with a string for each plot. And the first one defines what initial speed was, and the second one, the initial speed is slightly lower. Once the labels are defined, when you call the legend command, it will use those labels and it will insert the legend where it thinks it will not interfere with the data. You can of course also specify it manually where the legend is located. Finally, it's worth pointing out that if you're using a script or the interpreter to visualize your data, you have to ask it to show the figure explicitly, and this is done using the .show command. Can we edit the legend such that we have meters seconds to the -1 as opposed to meters per second? We can insert mathematics such as powers in this case using the label with a OR to define a raw string. And the raw string here will include dollar symbols to define a mathematical equation. And inside those dollar symbols, we can put any maths we choose using standard LaTeX symbols. Here we've decided to put meters.seconds, and the second is to the power of -1. We can of course also put such mathematical symbols on the Y or the X axis or anywhere on our figure. And in this case, with gamma, we can specify that the Y label is also going to contain a raw string, and the symbol for gamma is simply \gamma. If you're familiar with LaTeX for document publishing, you can of course use any of the standard LaTeX symbols within the maths environment defined by the dollar symbols. You'll notice here that we have a log scale on the y-axis. And log scales are very useful in visualizing data because if we have a basic linear scale, in some cases, it doesn't enable us to view the data in the most useful way, such as here for gamma as a function of velocity. Most of the increase in gamma here is towards the end of the velocity range. We can choose one axis to make a log scale using semilog, in this case semilog y. Reading the log scale is relatively straightforward. Starting with 10 to the 0, we have 1, and we can count each minor tick up the y-axis. From 1 by 10 to the 0, 2, 3, 4, and 5 by 10 to the 0, all the way to 10 by 10 to the 0, which is 10. Likewise, we have 10, 20, 30, 40, all the way to 100, and then 200, 300, and so on. Besides just a semilog on the x or the y, we can also define a plot that has log on both axes. This is referred to as a log-log plot. There are many other forms of two-dimensional data visualizations with Python, including bar charts. And here data is represented as heights of vertical bars. This can be called in Python using the .bar command. And in this example, we will visualize the function sine of x using bars, and it indicates a nice wave-like pattern which may be useful. Besides the default parameters of blue bars, we can also customize any of our visualization functions. And here we can add white boundaries to the bars and also change their color to magenta. We can also use histograms to visualize our data. In many cases, such data is statistical data, and the histogram enables us to see some underlying probability function. Essentially, a histogram counts the occurrence of given values in a list of data and visualizes the frequency of those values in the data set. The counting is defined in bins or ranges. And of course, you can customize your histogram function here in a variety of ways, including the color or the outline of the line. Here we've defined our histogram to use the step feature. An important feature of any scientific data visualization is the inclusion of error bars. With matplotlib, we can visualize error bars with our data using the function ERRORBAR. The ERRORBAR plotting function takes, of course, the XY data. Format of the symbols we've set to be a circle, and we define the Y error bars and the X error bars accordingly. We can provide an array of error bars or error values for each data point, or we can define our error bar using some numerical value. Format of the line is using a symbol or a circle in this case, and we'll see later that there's a variety of other symbols we can use to distinguish different data sets. This is enabled using line formatting. With my basic example here, I'm asking for a red dashed line where the data points are circles. Besides red, there's also blue, green, cyan, magenta, yellow, black, and white. The line types can be solid, dashed, fine dashed, or dot dashed, or just dots. The symbols, there's a variety of symbols including circles and triangles, and squares in different orientations. And these are requested whenever you call the plot function by defining the simple collection of symbols in the quote. You can also define the width of the line and the size of the marker within the plot function itself. With most visualizations, you will see that there may not be any minor ticks. And if you wish to include them on your visualization, you can request that these ticks are added by using the .minorticks_on flag. Beforehand, you can use the getCurrentAxis code to specify which figure you're referring to. In our example here, we looked at the sine of x function again, and in this case, we've added minor ticks to both the x and the y-axis. We can also define when these ticks occur and customize the labels on these ticks. To define where they occur, you can call the .set x ticks or y ticks to define, in this case, x ticks occurring at -pi, 0, and +pi. We can also change the numerical values to the symbolic pi symbols by, again, including a raw string. In this case, we're using the set x tick labels command. And now our x-axis is nicely formatted with our pi symbols. Besides 2D visualization, 3D visualization is tremendously important for more complicated functions. To visualize in 3D, you load a submodule called Axis 3D. And of course, as the name implies, this creates a third axis that you can use to visualize data. In the simple example, we'll visualize a sine and cosine function. But first, before we do that, we want to define a grid of x and y values. And this grid in x and y values we need to create into a mesh using the mesh grid function. Afterwards, we can then provide the uppercase x and y mesh grid points to any function of our choosing. In this case, the function we'll use is sine x plus cosine x. Once we have our function defined, next we want to initiate a new figure with some handle fig. We'll also make an axis handle from the getCurrentAxis command. This axis handle we're going to set with some projection equals 3D. And using this axis handle, we're going to call plot surface command, which we use to visualize the 3D data. In this command, we can also define the color of the 2D surface as red. We can also visualize this 3D data using a contour map. A contour map represents the three-dimensional data on a 2D surface. As the name implies, the surface map will have contour lines joining points on the function that have the same value. In this example, we're going to use the contour f. Now, contour f is a filled contour, so we're going to have the spaces between the contour lines filled with some color that represents the value of the function in that space. So contour f takes again the mesh grid variables uppercase x and y and our function f of x and y. As we can see, the color gradients indicate the values of the function, and we've customized also the figure to include a color bar. And the color bar also has a label that can be used to describe the function. You can see we go from a dark blue to a bright yellow for the range of function values -2 to +2. As with most details, you can customize the color bar to choose from a variety of different color maps. We can also visualize the same data using contour lines without the filled in areas. We can do this using the contour command. And again, we use the same syntax in the function call, including the variables and the function name. As you can see, it's much simpler, and the contour lines can be given labels to indicate what values of the function they represent. Here we customize the labels using the CLabel command to make the labels as a black font. Next, let's look at how we can create subplots in Python. Subplots essentially combine multiple plots into a 2D grid. The subplot command takes a number of arguments to define the size of the grid with a number of rows and a number of columns, and finally the position within the grid, reading from top left to right to bottom left and to bottom right. Here we've got a grid of 4 potential spaces where we can position our plots. For the first one, we define the position 1 in an array of 2 by 2, and here we're going to plot 2 lines as we shown earlier for the parabolic motion. Next, for the second position in the grid, we'll have 2, 2, and then 2. And here we'll add our semi-log on the y plot of the gamma function. For the position 3, we'll use our filled contour map of our sine x plus cosine x function. And to complete the example, on the fourth entry in the grid, we'll use our unfilled contour map of the same function. So it's relatively straightforward to build up a grid. In this case, we've got a 2 by 2. And typically, you may just have a single column, so a 2 by 1 grid, to have 2 subplots in a vertical fashion. Next, let's have a look at making double y-axis plots. And this can be very useful when you have a common x-axis, and you can use both the left and the right vertical axis to represent two different variables. Here we've got a parabolic motion where the blue line is the height and the red line is the velocity. Both functions are a function of time, so we can use our double y-axis to view much more data in the same space. As you can see from the code, the double y plot essentially uses the subplot command to create a single position in a grid. And on top of that single position, we'll have a double plot that will share the same x-axis. This sharing of the x-axis is enabled using the twin x command, which we applied to the new handle for the second axis, ax2. So ax1 and ax2 are the two axis handles, and using those handles we can then specify what we would like to be shown on each axis and what labels and so forth we would like to use. Finally, let's look at an important feature of visualization, which is saving the final result. Fortunately in Python this is very easy and very fast to achieve. Using the command savefig, we provide a file name. The file names can be anything from the vector formats such as PDF to the pixel formats including PNG and JPEG. It's worth looking at the differences between these two formats, and to do so we'll use a zoomed in image of one of our previous graphs of the gamma function. Here we have a zoomed in image of the y-axis, and on the vector format we can see that we are not limited by resolution as we zoom in. This is because all of the points and lines that make up the image are stored as mathematical vectors rather than pixels. And this enables us to effectively zoom to infinity and we'll still have the same visual resolution. While for the PNG or JPEG, even at very high resolution, such as 300 dots per inch, all of those dots are essentially pixels and they will have some finite resolution. When you zoom in, as we've done here for the gamma data, we can see that there are noticeable differences. While if you're planning on publishing your work and your analysis, it's recommended you use some vector format. And it will also save you on file size, since vector formatted files are much less memory intensive than PNG or JPEG files. A final feature in saving your file is to look at the boundary box. Typically, anytime you save a graph in Python, it will have an automatic boundary around the perimeter of the graph. This boundary box you can tweak and adjust to your tastes. Typically, we can set it to a tight boundary box, which minimizes the boundary to something that is functional without taking up too much space. Finally, let's summarize all of the new functions we've met in this video. Starting with the NumPy methods, we have introduced the load text and save text functions for loading and saving your data. Concatenate, vsplit, and transpose can enable you to manipulate your data arrays. Plotting methods, on the other hand, are quite numerous. For much of your purposes, you may simply just use the basic plot command or with error bars. But there are also the statistical visualizations with histograms, as well as the three-dimensional visualizations using plot surface and contours. And there are a large number of other functions that enable you to format your graph with labels and legends, and finally to save it.